So to continue with where we left off in class today, guys, with the electron configurations, with these blocks, what we do to figure out the electron configuration of any element is we start at the beginning of the periodic table and we place all the electrons in the element into the appropriate subshell. So, working on the case of vanadium, vanadium has 23 electrons that we need to place in the respective subshells. So we start up here and we start with the n equals 1 shell, and if you remember, then the n equals 1 shell only has one subshell, and that's the s subshell. So for that we say 1s, and then we place the first two electrons in there. So we kind of go across this periodic table and we place those first two electrons in the s subshell. Once you get to the end of a row in the periodic table, you start the next shell. So that's what these n numbers represent, is the shell that you're filling up. So at n equals 2, we start filling up the 2s because we're in the s block. So the 2s, then you place the next two electrons in the s subshell. And so the next one would be the 2s2. Then, after we've gone through the S block, we start filling up our 2p, so 2p6, so the next 6 electrons get put in the 2p. And you kind of track your way through the periodic table here. We're at the end of a row. We then start on the next one, and this will be a 3s2, 3p6, 4s2, so I'm just following along here. And at this point we have 20 electrons placed in the respective subshells. Then the last one, as we enter this D block here, this says that we need the D subshell that we fill up is one less than the row number we're in. So we're in row 4, which means we start filling up the 3D subshell, and so the final 3 electrons go into the 3D, and we'd say 3D3. So when you look at the configuration of vanadium, the whole thing would be written as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Now, I do want to mention that this is an ordering by energy. So when we order it by energy, you'll have the 4s2 come before the 3d, even though the 4s2, because it's in that 4 shell, the electrons in that are further away from the nucleus than the 3d electrons. The 3d is slightly higher in energy. You may have seen a way to remember this is to kind of write out all the shells and subshells in rows like this, and so you have columns and you have rows, and you start going diagonally across it, and that tells you the ordering. So it would be 1s, then once you're at the end of the arrow, you go back up here, 2s, go back up here, 2p, 3s, 3p, 4s, then you go over here, 3d, 4p, 5s. So I prefer to look at the periodic table, but if that helps you out, by all means use it. Also, I wanted to show you, I click on that. I want to show you the filling of each of these orbitals, of the separate orbitals, just so you can get a look at kind of how the electrons get represented in them. So the electrons in the 1s would be a spin up and spin down. Then the 2s would be a spin up and spin down. The 2p would be all paired up, and the 3s and the 3p. And so these are all increasing by energy, and we pair them up. And then finally we get to the 3D. And remember what Hund's rule says is that we need to put one electron in each orbital before we can have 2 electrons in any of them. So as we're filling up the 3D, we don't put, say, 2 electrons in this first orbital, then 1 electron. We have to put 1 electron in each of the orbitals, and we will have to do that until we have 1 electron in all of these 5 degenerate 3D orbitals, and then we can start pairing them up after that. Okay, so that is how we would do electron configurations. Again, I know you guys saw this sophomore year, so if you need to practice, look at those homework problems from your textbook and from the problem set, and practice doing those those electron configurations. All right, now there are some exceptions to these usual rules of just simply going through the periodic table, and that occurs when there's a possibility that by promoting electron from one subshell to another, you can make filled or half-filled shells. And it's hard to, predict when this is going to happen, but I do want to show you an instance where it does. One is for copper. Copper has the configuration 1s2, 2s2, 2p6, 3s2, 3p6. Now that's a lot to write out, and for reasons which we'll talk about in a little bit, it's easier just to look at those outer configurations, the ones that are in what we call the valence shell. So what we do is we summarize all of this with a bracket and argon. So we put the noble gas that ends the period right before that. So if copper is right here, putting bracket argon means take the electron configuration of argon and then just show what's called the outer configuration, so the electrons on the outside, because that's really what's going to determine the chemistry of an element, are those electrons on the outside. So bracket argon means the same electron configuration as argon, and then you just would start with 4s2 and then your 3d electrons. Now guys, this only works for the noble gases. You couldn't put like bracket nickel and then put one more. It doesn't work that way, okay? And you're only allowed to put noble gases there. On top of that, if I were to ask you for the configuration of argon, you can't just put bracket argon. You would put bracket neon and then 3s2, 3p6, okay, for the configuration of argon. So anyway, that's that notation that you may have seen before. And following that, you would expect the configuration of copper to have an outer configuration of 4s2, 3d9. So we have the two 4s electrons here, and then we would have 9 electrons in the 3d. However, what we actually observe is the fact that the configuration of copper is 4s1, 3d10. What it's doing is, since there's not a lot of difference in energy between the 4s and the 3d, it promotes an electron from the 4s. It spends a little bit of energy to take an electron from the 4s. It promotes it to the 3d, and then we will have a half-filled subshell, which is stable because now it's not being forced to pair up with another electron, so that stabilizes a little bit. And we have a filled d subshell, okay? And so the stabilization of promoting this compensates for the fact that we're going to have to spend a little bit of energy to do it. We also see this with chromium. With chromium, we have these paired 4s electrons, and then we have a 3d4 is what you expect. What we actually see is that electron goes from the 4s, it unpairs, and it gets promoted to the 3d. In this one, all these electrons are unpaired. They are not forced to be in the same orbital along with other electrons, and that does tend to stabilize things. So when exceptions do occur, that'll be why. You guys don't have to memorize these exceptions, but you should understand why they occur. And again, a lot of times it's to get these half-filled shells, which means that some electrons won't be forced to be paired together. Okay. The outer configurations we've talked about already. So something like mercury. Good gravy. Mercury would be. Let me show you where mercury is. Mercury would be all the way up here. If you were to do this whole configuration for mercury, you would have to do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10. Okay, that's a mouthful. We don't want to write all that out. So what we'll do is we look at this and we say mercury, okay. I'm just going to do the outer configuration, the valence configuration. There's electrons on the outside. So I'm going to put bracket xenon, which cuts out a lot of the inner electrons, which really don't do any chemistry for us. And we just look at the electrons that are actually involved with the chemistry. And so those would be the 6s2, 4f14, 5d10 electrons. Now, by looking at these outer configurations, we can understand why elements in the same group have similar chemical property, and it's because they have similar outer configurations. So once again, quantum mechanics explains why we observe what we observe with the periodic table. So if you look at these group 1 metals, you'll notice that they all have an outer configuration of S1. It could be a 2s1, a 3s1, a 4s1. And so all of these will have very similar chemistry. They all react with water to form similar compounds. They all form positive ions, +1 ions. And this is due mainly because they have similar outer configurations. Okay, so knowing quantum mechanics helps you understand the chemistry. Also, a little nomenclature here. For the representative elements, if you look at the number of valence electrons, the number of outer electrons, so is given by the number of the group. So for sodium, it's in group 1A, and you can see with sodium it has one valence electron. If you were to go with, shoot, I don't have the group numbers here, but this would be the 1A, the 2A, then 3A, 4, 5, 6, 7, 8A. So those tell you the number of valence electrons. Nitrogen would have 5 valence electrons, so it would have 2 of the electrons in the S and then 3 in the P, and all those would be in the same shell, and that would be the valence shell. And so we would say it would have 5 valence electrons. So for representative elements, once again, the group number corresponds to how many valence electrons that you have. Okay. All right. Now, as I was saying before in class, the atomic subshells, there are some nodes. So it's not just that they're only on the outside. There is some penetration to the inside. And so you'll notice that these 3D electrons, the majority of them are closer to the nucleus than most of the 3p, which are closer to the nucleus than most of the 3s. But these 3s, even though they're a little bit further away here, there are more electrons close to the nucleus than you would find in the p or the d, just due to the formula wave function. Okay, so I'll make you guys aware of that as well. All right, and this brings us to shielding, and this and atomic size are going to be the last topics for the screencast, because they're going on for a while already. But I want to talk about shielding, because shielding is the reason why the periodic trends are the way they are. So there's certain properties that elements have that we can predict how they're going to progress by moving through a periodic table. In other words, there's certain properties that as you move from left to right, they change in a regular way, and also going up or down a group, they change in a regular way. And we're going to talk about those properties and how we can use the periodic table to predict and compare differences in these properties. So for instance, we can compare the atomic size of various elements and kind of make a judgment on what would be the biggest and what would be the smallest atoms based on the relative positions of the periodic table. But the reason why we can do that is because of something called shielding. So when we talk about shielding, we talk about the fact that in an atom, we have those valence electrons on the outside, but we also have all those electrons in the inside. All those electrons that were kind of lumped in together with the noble gas symbol in the brackets. What they do is they kind of screen that nuclear charge from the outside. So instead of having the full nuclear charge Z, the electrons on the outside will feel what's called an effective nuclear charge, and that approximately is the full nuclear charge, the number of protons in the nucleus, minus the number of inner electrons. So if you take an atom like carbon, carbon has a nucleus with a +6. It has 2 electrons in the 1s subshell and in the n equals 1 shell. And by taking so these 4 electrons on the outside don't feel a +6 charge. They feel a +4 charge. Okay, so we would say the effective nuclear charge on those valence electrons is really +4. Now, that will have an effect because on these properties, because I'm going to go back to the periodic table here. Okay, so going back up on the periodic table, what you'll notice is that as you go from left to right across the period, you don't get any more inner electrons. So as I'm going across, say, period 3 here, I'm not adding any more electrons to those inner shells. And so the shielding will stay the same as I go across this row. However, I keep on adding more and more protons as I go across the road. So the effective nuclear charge will actually increase as I go from left to right across any period, because the shielding stays the same, but my nuclear charge will increase. Now, because my effective nuclear charge increases as I go from left to right, that's going to attract those outer electrons more, and that will give me a smaller atomic radius as I go from left to right. Okay, just because it's going to feel more of that positive charge from the nucleus because I have more protons without adding any more of those inner electrons. Now, as I go down a group, so as I go down a column here, what's going to happen is I have more protons being added still, but I also am increasing the number of these inner shells. So as I go from 2 to 3, I'm adding a whole another approximately 8 inner electrons. okay, to compensate for my plus, my increase in charge by 8. So what we see here is that the effective nuclear charge as we go down a group is the same. Okay, it's not really going to change. But what does happen is because we're filling up a higher n number shell, those n number shells are further away from the nucleus. So just from that fact alone, the fact that we're filling up a higher number shell means that those outer electrons are going to be further away from the nucleus and the atomic size will increase going down a group. Okay, so because of shielding, the first periodic trend that we're going to talk about is atomic size, and as we go from left to right, the atoms are going to get smaller. As we go up to down, they're going to get larger. Because going this way, we increase the nuclear charge, the effective nuclear charge, which attracts those outer electrons more. And going down, the effective nuclear charge is the same, but we're filling up these higher number shells, which are just naturally further away from the nucleus. Now, the way that we measure atomic size, let me get down to this. Okay, so the way that we measure atomic size, there's a couple ways, but usually what we do is we take a homonuclear diatomic molecule and we take half of that bond distance, and so say we have an H2 molecule, just taking half that bond distance we say is the atomic radius for hydrogen. Okay. Now, as I was saying, the periodic trend going across the period, the shielding remains the same, but the Z increases, that nuclear charge increases, the effective nuclear charge increases, and the atomic radius will decrease going from left to right. And I really do think it helps to know why these things occur rather than just trying to memorize these facts. If that's what you have to do, go ahead. But I would much rather you guys understand why it does this, and I will ask you questions on the test to see if you know why. Going down a group, both the Z, the nuclear charge, and the amount of shielding increase, but N increases as well, which results in the valence electrons becoming further away from the nucleus, and the atomic radius will increase. Okay, so if you guys understand shielding, you can understand atomic radius, and then tomorrow, I guess Wednesday, when we get to this, we will talk about ionization energy, electron affinity, and relate those back to shielding as well. Okay, so thanks for listening to this, guys. I know it was kind of a long one, but I will talk to you later.